And let's talk about durability. Durability, in a nutshell, is the process of persisting the writes that clients make to the database to a non-volatile storage system. That means anything that we write is stored. So that means even if I lost power, or even if I crashed as a client after my committing the transaction, if I come back, I see that change. If the database crashed after the commit, I restart the database, I see that change. I see it persisted in disk. If my computer crashed, I come back, I see this change. That's what durability is. And you might think of that as okay, of course, everything is durable. Not really. A lot of database systems actually play with that. They play with the durability. It says, okay, durability is slow, right? Because to make things durable, that means you have to persist them to disk, and disks are inherently slow. So a lot of databases play around this durability and say, okay, I'm going to write my stuff to memory, and occasionally on the background, I'm going to snapshot and write to disk. So I'm going to make my writes faster. Can you get the database that does that? Redis does that, right? As an option, obviously, right? But durability is one of the strong relational databases must have, right? You have to be durable, right? And we're going to define what that means, really. So durability, changes made by a committed transaction, emphasis on committed, has to be committed. If it's not committed, really all bets are off. Must be persisted in a durable, non-volatile storage like SSD or hard drive. Durability techniques. There are many durability techniques. There is the WAL, the write-ahead log, which really, when I show you all these tables and indexes and stuff like that, these are really the representation of the data, which is what people read, what clients read. But these are really large if you think about it. So if you really write these things to disk, which we will, durability, committing a transaction takes time, because this is huge. These data and the data structures and the B trees and stuff like that, it takes time. So what databases implement is a version of the changes that happen only, which is deltas effectively. You can think of it as deltas. And then this is a write-only write-ahead log, which calls WAL. Any changes goes to this immediately first. We flush it immediately to disk. And this guarantees persistence. So yeah, we didn't really update the data table, right, on another data structure yet, but we can, if we have a crash, we have this beautiful WAL, we can go back and read all the WAL entries and then rebuild this state effectively, easily from a persisted state. We still persist this, we still write this durable, right, to disk, like the actual table itself, the changes, but we don't rely on that because that could be slow. And there's the another approach, which is asynchronous snapshots, or even synchronous snapshot for that matter, where as we write, we keep everything in memory, but then asynchronously on the background, we snapshot everything to disk at once. And that is also another concept. Redis uses actually both of these things. Append only file is another option, which is very similar to the WAL, really, that Redis uses, right? Which is keeps tracks of the changes of what happens and then writes these things. This guarantees that we have a very, lightweight way of storing data in a very fast way, but also in case of a crash, I can always read back and construct the state of the table completely without the need of storing the likes and the ID and the string and the blob and all that stuff, right? We store only these changes, and eventually we're gonna write that as well. So let's talk about the WAL a little bit. Writing a lot of data to disk is expensive, as I talked about that a little bit. We have indexes, we have data files, we have columns, we have rows, we have system files, system tables, all this stuff. If you imagine writing all the changes and the amplification of the writes itself, that's going to take a long time. You can do it, but it's going to be slow. So we need a better way. We need a more optimized, compact way. So they compress this version of these changes known as WAL, write ahead log segments. So they only write these log segment, and this this better be persisted, because this is what tells us what to change effectively, right? So these are just tells, hey, we changed this value to this, we changed this value to this, we changed this value to this, and we even compress that, so we get it in a very tiny segments. So there's something very critical in database systems, and this is one of the problems that operating systems do, and this is called the OS cache. When you actually write to the OS, you ask the operating system, whatever this, Windows or Linux. When the database asks something to ask the OS to write to disk, the OS actually does something shady. It writes not to disk, it writes to its own memory cache, right? And the reason is because it want to batch these writes and flush it to disk at once for performance reasons, because most applications does a lot of writes, and they want to kind of batch these writes and do it once. So because if you batch it, you do less IO, and if you do less IO, as I always talk about, this IO is better. But what's the problem with that? What if you say commit, and the database asks the OS to write the WAL segments to the disk, but the OS, they say, hey, I'm going to write it to the cache instead. The OS will tell the database that, hey, I wrote successfully, despite it only wrote to the cache. It didn't write to the disk. It will tell the database that, hey, database, or the application, it doesn't know it's a database, just knows it's an application that asks it to write something. And it will ask the database, hey, by the way, I'm the OS, and I wrote your changes successfully, but it only wrote it to the cache. So the database will say, okay, sure. The database will say, your transaction committed successfully. But the problem is, what if you get a crash there? The database told us it committed successfully. You get a crash, your computer will crash, you restart, and then the OS, obviously, the data was in the cache, on the OS cache. When you restart, it was in the RAM, obviously, so we lost the data, and as a result, the database lied to us. The database in that particular situation is not durable, because you wrote the transaction, because the transaction told us it was committed, but it wasn't durable. Why? Because of the OS problem here. So when the writes go to the OS and the OS crashes, machine restart could lead to loss of the data. And that's a big problem that databases fight for. So there is this command that bypasses the OS cache and asks the database, ask the operating system, hey, you dumb OS, I don't trust you. I tell you to flush these WAL changes, flush them directly to the disk. This is called the fsync command. So fsync command just forces the write always to this. So it's going to be slow. It's going to be very, very slow. So we have to do it with in a smart way, because you're bypassing the OS cache. And you might say, why this the OS uses the cache, right? Isn't it dangerous? Well, most of the situations, like, you don't really get a crash that often. So if you save a Word file or a notepad or something, things like that, it's okay to use the OS cache. Most of the applications use the OS cache, and it's very rare that this crash can happen. Database systems are different. They want to guarantee durability, and as a result, they have to bypass the OS cache. And as a result, it becomes slow. You see the trade-off, guys, right? There is always a trade-off. So fsync can be expensive and slow down commits, right? This is another problem, right? If you commit, you want to commit as fast as possible. So let's summarize the final lecture here. Durability is the ability to persist the changes when the transaction commits. The emphasis on the when transaction commits. So when the transaction commits, I want you to persist it on disk. I don't care. I don't care where you persist it. Here's what I want. When you tell me it's commit, I can shut off the power at that exact moment. And when I come back, my data better be there. That's what durability means. I don't care. You're gonna store it on the disk, on SSD, on the storage, on I don't know, in the air. Who cares? I don't care. I want my data back. That's what durability is. A lot of databases play trade-off with these properties because durability is slows writes down, because now I'm going through this physical medium to process my changes, right? And as a result, it will be slower than if you wrote to memory. So Redis, for example, plays some games with that. It gives you option, actually, that none of the databases that I know of, even relational, gives you that option. Because guess what? It gives you the option. It says, hey, you want to be completely durable, strongly durable, or you want to be partially durable? Not even partial. Partial is the wrong word. Eventually durable. I guess I just made up that word. But eventually it's going to persist to disk. So there is a slight few seconds delay that if you lose power or if you crash, you could lose your data. Some people trade that off, that 3 seconds, with fast writes, because hey, I'd rather get fast writes, and okay, my data is not that important. I'm storing just logs of my application IoT devices. So who cares if I lose a few things? But guess what? Redis, most of the time, nobody reports loss, right? Because crashes are very rare if you think about it. When it comes to the actual databases, those guys build the systems to not really crash. But you cannot take that guarantee, because if Morphe is low, right? It says if it never happened, it will eventually happen, right? All right, guys, that was the last lecture of this. We're going to jump into many other lectures. I'm going to talk about eventual consistency. I'm going to show you examples here. So go with another lecture. It's called Acid Example by Practice, I believe. That's what I called it. And see how I do this in real time with the actual database. Show you all these beautiful properties. I'm going to also talk about eventual consistency, and I'm going to take a stab at the quiz and enjoy the rest of the course. Thank you so much. Goodbye.
Hey guys, what's going on? So we have talked about ACID, the 4 properties, in a theoretical manner, but it's time to put them in practice and explain those 4 properties in an actual database setting. So I'm going to pick Postgres, but you can do the same exercise with any database you want. For simplicity, I'd like to use Docker, because this way I can try out many databases with just one command, and I have spin up another database just like that. So let's go ahead and spin up a database right here. You know what, I'm going to keep this up because I'm going to need the 2 terminals, but I'm going to spin up a new one right here. And let's spin up a Postgres container. I'm going to do Docker run. Let's call it Docker run. Let's give it a name, dash name. It's going to call it acid. Let's go PG acid. Then we're going to do, we don't really need to expose the port or anything, because we're going to really go into the container itself, bash into the container. The next command is, let's go ahead and detach that. And then let's pull up Postgres 13. I think that's the latest thing, right? And before we run that, actually, we forgot something very important, which is -e Postgres password equal Postgres. You have to give a Postgres user a password. Let's go ahead and run that. Just like that. It's going to take a little bit while on your end to load the Postgres image, but once you have it, you're ready to rock and roll. Let's go ahead and so let's make sure that the container is running. And just like that, yes, here's my PG acid. It's running. Always make sure that it's running, because you might have spilled something in the command or did something. If it's not running, something is wrong, right? So let's go ahead and do docker exec -it, and then get into the PG acid. And what command do we want to execute? psql, because that's the Postgres SQL command. And I want to log in as -u, the Postgres user. And that, just like that, we are in the Postgres command shell. Now we can execute beautiful stuff. We can create a database. We can play with that, create tables. So since I'm in the Postgres database, I have a database called Postgres. So I'm going to play up with that database right there, right? So let's go ahead and do create a table called products to test atomicity, right? I'm going to go ahead and create table products. Let's do a PID serial. So that's an auto increment in MySQL, I think it's called. And sure, let's make this the primary key. And I think we can just continue doing that stuff, right? In a new line. And name as a text. Boom. What else? Price is double. I'm not sure it's double or float in Postgres. I keep forgetting in different databases. When you work with many databases, you get confused. And the finally is inventory. How much inventory do we have in this product? And then let's just use an integer here. And that should be it. Yeah, that's what I thought. It's not called double. It's gotta be float, I think. There you go. I think it's double in MySQL or Oracle. I keep forgetting. All right, now we have a products table. Let's go ahead and create a sales table so we can produce sales. Create table sales. Let's go ahead and do a sale ID. That's a serial. Also primary key. Let's hit enter. The primary key, that's the product ID. I can create it as a foreign key, but it doesn't have to. So that's an integer. All right, that's a product ID, integer. Boom, price float. We learned our lesson. So that's an entry in the sales. What could be a product could be sold in a different price, right? But the current price of the product is in the product table. This is what was sold at, right? And then the quantity as also an integer. And boom. All right, now we have these two beautiful tables. Let's test out atomicity. So first thing, let's populate some rows on those tables, right? So I was going to do insert into products, and let's give it a name. I don't know. What are we inserting? Name and a price and inventory. For simplicity, I'm just going to do one row here. Let's call this a table. Table's very confusing. Phone. I don't know. You're selling phones, and the price of the phone is $999.999. That's an expensive phone. Inventory. Let's say you have 100 units, and then boom, and then that's it. That's the only product we have. Okay. So now let's test out our atomicity. So, I mean, if we did select star from products, you can see that we have this row, right? What we're going to do is we're going to make a sale. We're going to sell, let's say, 10 phones. Like we sold 10 phones. What does that mean, right? If you're working with domain-driven design, that is one task, right? But it's in the database, it's broken into multiple queries in a single transaction, right? So a sale is of 10 units. That means you have to deduct 10 units from the inventory, and then you have to insert a row in the sales table saying that you have inserted that. You cannot do that in two transactions. You have to do it in an atomic transaction. That's what we explained in the video, right? In the lecture. So let's go ahead and begin a transaction. Boom. And then the first transaction we're going to do is update products. All right. What was the phone ID again? Let's just do from products. You might want a query, so process ID number 1, process product ID number 1. So what we're going to do is update products, set name, update products, set inventory equal inventory minus 10, right? Boom, that's in this transaction. So now if I query that product again, you can see it's 90, right? Very, very critical here. So now if I go ahead and insert, let's assume I crashed right here. If I crashed right here, what will happen? You just lost 10 units from your phones that you didn't really sold, okay? And that's the idea of atomicity, because you have to follow it up, right? So like, let's say I crashed right here, like, I don't know, just killed the whole container, right? Just like that, right? If you do that without atomicity, it will be a disaster. If you come back to the database and then you said select star from product and you saw that it's a 90, but no, it says it's 100. Why? Because of atomicity. We started a transaction, we did an update, but we crashed. We exited Postgres in this case, simulating a crash, right? That is the idea of atomicity. All the transactions have to be done in as an atom, right? You cannot split those. Okay? Let's do the transaction again in the right way by doing begin transaction, doing an update to the inventory, and then now I'm going to insert a sale. Insert into sales, process ID, price, and quantity, right? Let's just do boom values. Number one, I sold it at, like, I don't know, I sold it at 999.99, same price. And I sold 10 units, right? And you can break it up into 5 units at this price and 5 units at this price. Who knows, right? Unless we did that. Now, if I do query the sales tables, you can see that we have 10 beautiful units right here, and my products are 90. So now, if you sum those puppies up, you get 100, and that's called consistency. We just explained atomicity and consistency in the same concept, right? And this is only viewable in my transaction. So now if I went to a completely different terminal and try to query, again, I'm not committing yet, right? And I do it like, I don't know, let's do the same thing. Hopefully we have, so let's go there, PG acid. And then if I do select star from products, you can say that's still 100. And if you query the sales table, there is nothing. And that's part of isolation, right? Because now we're in an atomic manner. So these two things were inserted in that transaction, but we didn't roll back or commit, right? The moment I commit, now we have a nice view and of the data, and the data is now flushed and available, visible to all transactions. Now, if I query it again, you can see that we have a sales now. It's not 0, so there is a 1. And if you query the products table, you can see there's 90. So what we're talking about here, talking about atomicity, we talked about consistency, because if you don't have atomicity, you don't have consistency. And you can argue with that, obviously, guys, because you can say, hey, no, I can be smart and make a single query, right? And then for the longest time, MongoDB, for example, didn't have atomicity across documents. It has only atomicity across a single document. And people were fine with that, because most of the time they will do their data model so that it is a single document instead of let's say normalized like we do here. All right, let's jump into isolation. All right, guys, so I went ahead and inserted a few rows in the table. You don't have to see the process. I'm going to cut it out. It's a straightforward thing. We sold a couple of units right here, a couple of units right here. So now let's test out isolation. And to test out isolation, guys, I want to do the following, right? So to test out isolation, guys, I want to do the following, right? Just with normal transactions. I'm going to start a transaction in my first session right here. And I'm going to do a normal query saying select product and the count of the product. All right. I just want to see how much sales did I made or for each product, right? From sales and group by PID. Boom. If I do that, all of a sudden now in this query, I have 3 sales for product 2 and 3 sales for product 1, which is pretty good, all right? Now I want to actually print the report that shows that what are this list, just the whole thing. So in order to do that, you do select product, price, maybe you do a join, but we're not gonna do that. Quantity from sales, that's it, right? But before you're gonna execute it, another session started right here, okay, and inserted a new sale. Okay, you just inserted a new sale, right? And you are just doing your own thing right here in generating this large report, right? But you reach this stage, and meanwhile, think of these two as concurrent application transactions going at the same time. Someone is making a sale, someone is generating a report. So in the same time, I'm gonna generate a new sale. Hey, we just sold a new phone, right? PID, and let's say price and quantity, right? Values. We sold a new phone, right? And at a price 999, the 99. Yeah, let's just say we sold 10 more phones, and we also go ahead and update the products where set set inventory equal inventory minus 10, where PID equal 1, because we just made a sale, right? So we need to decrement it. And then what we did is like we actually committed. We're done. We made a sale. And if we went back here, we're continuing to generate the report. Again, this is happening in parallel, right? I'm pausing it just to show you. But this is, now we made a sale, and then you printed the record, right? So you printed that you made three sales here, and then you actually printed that stuff. And guess what, guys? This don't match. You said that and this happens a lot, right? In actual companies where the actual table doesn't match the counts. And this happens if you do this kind of things. This I'm going to talk about. This is called isolation. The concept of isolation. We're not fully isolated here. So what happened here is we printed this puppy, right? And we said, okay, we made 3 phones, actually 4 phones, and 2 and 3 earbuds. So the earbuds are correct, but the phones are not correct. You just produced an inconsistent view. So inconsistency or consistency in general can happen because of atomicity, which we explained, and can also happen because of isolation, which is what I'm about to explain here. So how do I make sure that nobody touches my view when I am beginning my transaction? If I am starting this transaction, I want you to give me a snapshot, right, of all the queries that I'm going to do as if at the moment of where the transaction started. And that's called repeatable read. So let's go ahead and roll back this thing, right? And then we'll do a begin transaction, but we're going to do isolation level repeatable read. I think that's how you say it. The default was read committed. What that means, anything that has been committed on other transaction, I can see it. And this isolation level works most of the time, but sometimes in this case, you don't want it. You want a repeatable read or serializable. So let's go ahead and start in a repeatable read. And now, if I'm going to make my beautiful query, the count, hey, there are 3 and 4, which is good. So we made 4 sales. But look at that. I'm about to execute the second query to query the sale. But in the meantime, someone started another transaction. We don't care which isolation level at that point, but they inserted another sale, same sale exactly, and they committed. So they just made another sale. But if you query this, notice that it didn't show up on your case here. Why? Because your isolation level prevents you from seeing stuff that other people is changing. That's a beautiful repeatable read. It's expensive. You gotta understand how it works, right? Because it works at the MVCC level, and Postgres does it differently. MySQL does it differently. SQL Server does it differently. Oracle does it very similar to MySQL. Actually, MySQL does it very similar to Oracle, if you want to be very precise. But that's it. Now, if you have a consistent view, you made 5 sales technically on the iPhone, but if you query again that group by, you only see 4. Go ahead in this other query, right? If another session, if you do select PID count PID from what is that? So we have 5 units here, but here, no matter how many times you execute that, you're gonna get a repeatable read. Your read is repeatable; it's not gonna change, and that's a very attractive feature for a lot of applications, right? So now, once you commit or roll back, you're done. If you execute that query again, you see 5 because you're out of your transaction. All right, guys, that was isolation. Finally, for the fun of it, let's do this. Guys, exit right here, and then Docker. I'm gonna do this. I'm gonna begin a transaction, and then I'm gonna insert a new product. To explain durability. Insert new product, and I'm gonna prepare here to kill the container, the whole container, pg stop, right? But in the exact same second, I am going to insert a new sales and see if this is actually gonna happen. If I say, if it says commit, what will happen here? Name, price, inventory. Yeah, let's just insert a new product. That's called TV. Yeah, $3,000. And there is only 10 units of this. And I'm gonna do this, and I'm gonna commit, but at the same time, I'm gonna kill the container. See, immediately we were killed. So now, I wanna know, did my TV get recorded? The Postgres did told us that it's committed, right? If I do this, and a lot of database doesn't support this, by the way, like Redis. Redis is an in-memory database, but it does support persistence, right? But essentially, a durability it means if you tell me that you committed something, that means if I log in again, it better be there. So let's see if is it there. Yep, it's right there. Because it told me it committed, if it didn't return the commit, that means it hasn't been written, right? And durability is a very, you might think of it as like, okay, of course, Hussein, it's given that it has to be, if I write something, it has to be there. But no, some databases write to memory first for a performance reason, and if the container or the host dies, they forget to flash to disk, you just lost your stuff. But guys, what do you think about this, guys? Thank you so much for watching. Have fun. Enjoy the rest of the course. And I'm going to see you in the next one. Goodbye. What is going on, guys? My name is Hussein, and today I'm going to talk about a very interesting read phenomenon in databases called phantom reads. And this is something a lot of people overlook, and it can, if misused, lead to a disaster. So let's just explain what is that. Phantom read is one of the 3 phenomena, which is dirty reads, non-repeatable reads, and the phantom read. Happens in concurrent transactions. So when another transaction does something and you're in another completely concurrent transaction running at the same time, and you're seeing unpleasant results, let's put it this way. So phantom read explicitly is when another transaction inserts a new row, and all of a sudden, when you do a query in your own isolated transaction, you start seeing that row despite you shouldn't really see that row. Like, let's give an example so this is all clear. So I'm here, and this is the transaction number 1, this is transaction number 2. There are no any transactions yet, it's just terminals. But if I do select star from sales, I have a sales table here. You can see that I have 5 records here, right? This is the dates and all that stuff, right? So now if I do a begin transaction here, I started a transaction, and I do a select star from sales, you can see that I see these 5 sales report, and I'm about, let's say I started the transaction to produce a report about all the sales that I made between these dates, and let's say I want to do the sum, right? Let's do, okay, select PID, sum of the price from sales, and let's do a group by, you have to do a group by PID, and all of a sudden you have product number 1 sold $40, right? So now if I go, I am still on a transaction. I go on a completely different transaction, and I'm going to insert a new sale. Someone just made a sale, and it happened to be between these dates, right? Say PID, price, date, values, enter. Let's just say product number 1, it made up, I don't know, $15, and it was made on February 7th, 2021, right? And now I was in a transaction, so this automatically started transaction, committed, right? Did the statement and then committed immediately. Now if I go back to my isolated transaction, so they say, right? And I do a query, all of a sudden the sum has changed. Remember, you're producing a report, and the report has to be consistent based on the start of the transaction. So if people starting making sales while you're producing a report, you're gonna get funky results. Like, let's say you're listing all the products and then you're doing a query to do the sum, you're gonna get an inconsistent result. Of course, you're gonna get an inconsistent result. Now, if I do select star from sales, and even if I do a range query, let's say between this and this, you're gonna get this extra row that had been inserted. This, most of the time, is undesirable. Right? So how do we fix this? Postgres provide us with ways to fix this, and most databases actually do, and that is called isolation level, which I talked about in my Introduction to Database Engineering course. So now the serialization isolation level allows the databases to serialize transactions so that nobody, if a transaction has dependency like this one, this has a dependency on this insert, it will affect it. If Postgres detects, or MySQL or any databases that supports serialization detects that there is a dependency, it will try to isolate those changes. So let's go ahead and be in a, let's do the same thing, but in an isolated, let's do a rollback first and then do the serialization. So if I do begin transaction, isolation level, serializable, and now I am in a transaction that is serializable. That means anything that I read must not depend on other transaction that is currently running. Otherwise, things can go bad. So if I do select star from sales, you can see that I have 6 records. Let's go ahead and insert something in a completely different row here. Let's insert the same thing. Sure. Now if I go back and a query, you see that I've been isolated from that. Postgres detected that, hey, something happened on the other end, but don't worry, we have isolated you from that change, okay? So now you can safely commit your change and you're good, right? You can produce a report, you can do the sum, and you'll be isolated. You will not see that change that happened on the other transactions. So finally, this is all true in all databases except Postgres. Actually, Postgres is special when it comes to this. Postgres prevents phantom reads even in other isolation levels, such as repeatable read isolation level. Right? So the repeatable read is allow you to execute the same query yet get the same result. Right? It's a little bit different than phantom read. Phantom read, all of a sudden you get a new row. Read is just you're reading a value, and that value does not change no matter how many times you query it in the same query, in the same transaction. So now I begin my beautiful transaction here, which is non-repeatable read. There is 7 rows now. Why? Because now I started a new transaction. I picked up the latest changes. It's almost like it is implemented as versioning, because MVCC, multi-version concurrency control. So when you start a transaction, you create a version. That's a version of these rows. And then as you start editing other people committing, the database increases its version. So now, even in repeatable read, if you do this thing, that phantom thing, you don't see that phantom read. That even in arrange queries, whether this is an unbounded query like what I'm doing right now, or if it's like you're doing between, hey, give me the sales report between this date and this date, that's also can be affected as a phantom read. But if you're on a repeatable read isolation level, you do not see that even in Postgres. That is very special only to Postgres. MySQL, if you do a repeatable read, you don't get rid of phantom reads. That's very, very critical. The only way to get rid of phantom reads in Oracle, MySQL, SQL Server, as far as I know, you have to do serializable isolation level. Or you do some sort of a pessimistic locking, right? So it's like, hey, lock until if someone is changing the stuff, don't allow me to read it, right? That's another way. All right, guys, very quick video to talk about phantom reads. I'm gonna see you in the next one. You guys stay awesome. Goodbye. Hey guys, in this video, we're gonna describe the difference between a serializable isolation level and non-repeatable isolation level. I've searched the web and there are very, very, very little resources talking about this. So I wanted to make a video to talk about the difference between them, and then why would you pick serializable isolation level over non-repeatable? Let's jump into it, guys. So here's an example where you have a read committed or a non-repeatable isolation level. Okay, so let's say we have a table, we have AA here as values and BB here. Okay, so you assume this is a table of field and these are just 4 values, 4 rows with these kind of values. Transaction number 1 changes A's to B's. Transaction number 2, the green one, changes B's to A's. So it's literally update table set field equal B where field equal A. And the other one is the reverse. So what happens if they execute concurrently? So both of them start at the same time, and then this transaction starts. Obviously, it changes all the A's to B's, and so it's only going to touch these 2 rows, so it's going to become BB. However, the second transaction, its view, current view is it's reading AABB, and it's going to query and find that these are the 2 B's, and it's going to change them to A. So technically, this transaction changed only these 2 rows, this transaction changed only these 2 rows, so they did not step on each other's toe. So there is technically no concurrency issue if you thought about it, right? So non-repeatable read will not catch anything. Says, hey, you guys didn't step on each other's toes. Like nobody edited anything, edited the same value on different transactions. So that's fine when it comes to read committed and non-repeatable. But that leads to a result that is as like this, BB and AA. It's like almost flipped. Maybe this is what exactly you want. But sometimes this is not what you want as a user in this current domain, right? This is what you want. You want the transactions to be actually serialized. No, I want no. If there is dependency when it comes to reading and writing, and that can change the result, I need you to be serialized, as if like each transaction are physically executed after each other, almost physically executed. The databases don't implement it this way, but this is how serializable look like, at least. So in this case, when we start with T1, we change all the A's to B's, and then, okay, we only touch these B's, right? So that will obviously, transaction number 1 only touch this row. But when T2 starts, it has a different view of the database. It has a different state. So when it looks at that, oh, all of these guys are B's, so I'm going to read all of them, right? So it started with a different version, if you will. And now all of them will be A's. And based on where you start, if it's transaction 2 starts, you're going to end up with B's, right? So that's what we're going to explain. Let's jump into the actual Postgres terminal and explain the stuff. So here, guys, I have my beautiful table that is called test. And this is the BBAA. That's what I have today, right? So what I want to do here, I'm going to begin a transaction that is, let's say, a non-repeatable read transaction. So I show you the problem first, right? And let's do it. Begin transaction, isolation level, non-repeatable read. Let's confuse those two. And then do the same thing here. Begin transaction, isolation level, repeatable read. Both of them are repeatable read. So those guys, this guy says, okay, update test set t, the field, equal a, where t equal b. And then we're going to copy the exact same statement so we don't have to type it all the time. And then go to the other one and then change b's to a's here. If I do that, obviously we're on a non-repeatable read. So if I do select star from test, I get all a's. If I do select star from test, I get all b's because I'm isolated. But now, let's say I commit here, and then I commit here, and then I do select star from A, test. Look what we get. We get select A, B, B, select star from test. We get the same state essentially because the rows that changed didn't overlap. But this is not what we want, as we showed. I want these puppies to be serialized so I can get all A's or all B's. That's what I want. So let's start a transaction that is called isolation level serializable. Serializable. Can't spell this thing, man. All right. Begin transaction isolation level serializable. All right. So now we're in a serializable manner, right? So now if I query, all right, my table is AABB, right? So it's almost the same state. So now I'm gonna do boop boop. Hopefully it's still there, the query. Nice. I'm gonna change all my A's to B's. Boom. And now I'm gonna change all my B's to A's here. And now I'm gonna commit. Look what will happen. Committing here says, okay, that's fine. I commit you guys. You get all B's. But now the other party will want to commit is, hey, this is my one to change. But look at that. Postgres says, nope, babe, nope. Could not serialize access due to read-write dependencies among transactions. Reason code, cancelled on identification as a pivot during commit attempt. The transaction might succeed if retried. That is the case when you do an unrepeatable and serializable. You have to be prepared as an engineer, a database engineer or developer, to retry the transaction in case of these failures. Because what Postgres is doing more work, is actually looking for dependencies. And it's doing some magic here. That's like, okay, you're writing something that this guy is reading, and you're writing something that this guy is reading. I cannot let you commit this stuff. And since you are in a serializable isolation level, to guarantee that serializability, sorry, I cannot let you commit. Fail, do it again. So this transaction now has been rolled back. And then as a result, I get this state in this case, which is almost what we want to do. So now if I executed this again, right? Let's go ahead and do begin transaction, boom, and I do boom, and I do commit. It's not going to yell at me because no other transaction are in transit, let's say. So if I do that, we get all A's. And that's exactly how serializable works. If you want to do serializability, prepare to get failures, right? There are other ways to achieve this by doing pessimistically obtain lock. Right? Say, hey, this puppy is mine now. I'm gonna obtain select for update, whatever, right? So hey, don't touch this stuff, right? So all other transactions just waits. But you have to be in a read committed isolation level for that to work, right? So it gets a little bit complicated. But I just wanted to explain these two isolation levels, guys. Let me know in the comment section what do you... All right, guys, I just wanted to explain these two isolation levels. Hope you enjoyed this. I'm going to see you on the next one. You guys stay awesome. Goodbye, y'all. Consistency is the property of having expected results in the view of the data or during reads while working with a database system.
It is one of the ACID properties in relational database systems. Eventual consistency is another term that was born recently, specifically as a NoSQL databases started to emerge. In this video, we will discuss and talk about the different kind of consistencies, and we will explain what eventual consistency mean, how both actually relational databases and NoSQL databases suffer from this eventual consistency. And this is something that is not very clear out there, right? So a lot of people think that eventual consistency is something for just NoSQL, right? But that's not entirely correct. If you want to find out how that is the case, stay tuned. Here's the agenda. Here's what we're going to talk about today. In order to talk about eventual consistency, I really need to talk about consistency. And I have two types of consistency here to discuss, and it's very critical to disambiguate these two types of consistencies. Okay, and then we're going to talk about eventual consistency. But let's learn about consistency first. So you can have consistency in your data or consistency during the reads, and these are two separate concepts that we really need to understand. I'm going to talk about each of them now. Consistency in the data specifically. Let's take an example here. And it emerges when you have multiple views and representation of your data, especially with multiple tables, foreign keys, joins. That kind of consistency emerges when you have these multiple collections of data. Okay, that represents kind of the same unit. When you have essentially a normalized view of your data. Let's say an example. Let's say this is Instagram. I have a table called pictures. I have an ID of the picture, the blob, and the total number of likes that this picture received. And there's another picture, another table that actually lists all the users who liked what pictures. Okay, makes sense. So if theoretically these two views present the same thing, which is a picture and users, right? But in reality, those two better be consistent, right? That means if picture one got 2 likes, that means if I go to the other table, there must be 2 records, okay? So that's a consistent view of the data itself, okay? And there are a lot of things that ensure this kind of consistency, especially when you're updating multiple things. And relational databases are great for this, especially with atomicity and isolation. It makes sure that you're touching as much as table as possible, and it's going to ensure that consistency for you, okay, in the data. Let's talk more about that a little bit. Consistency in the data is defined by the user. I split those two views into 2 multiple tables, the pictures and the user, like balance sheets and the sales, all that stuff. You split it up and you normalize your database the way you want, but it's essentially defined by you as a user, and the user here is essentially whoever designed the database, right? You get referential integrities, you get foreign keys that represent those tables. You delete one, if you delete the picture, right? In the back example, if I delete this picture, all those records will go away, right? If you have cascade set on your foreign keys and all these things that ensure your consistency in your data, in that view, in that simple view, narrow view. Okay, atomicity and isolation are two properties of the database, relational database, that ensures, if you think about it, this consistency. And we talked about this, but essentially atomicity is like all or one. If you have a transaction with multiple queries touching multiple tables, all of those should fail, right? If one of them fail, okay? And if all of them succeeds, that gets committed. NoSQL databases, most of them do not have that atomicity on different views. They have atomicity on a set of collection. If you're updating a collection, that's all you get. If you're touching other stuff, you cannot really ensure atomicity on that. Isolation is the ability, is like, if I am in an in-flight transaction, can changes to other stuff being seen by me? Like if other transactions are executing transactions or changing, can I see these changes in the same time? Okay, and that obviously leads to inconsistent reads, inconsistent results. Okay, we talked about that in the other video as well, right? Different kind of isolation, repeatable read, and non-committed, and all that stuff, serialization. Let's talk about the Second type, the read consistency. If I have a database here, okay, and I say, hey, database, update this field, set it to value X, okay? And then if I do that, that value will be updated X. And consistency in read is nothing but if a transaction now comes and try to read that value, it better get that new value. That's what consistency in reads mean. Now we say, Hussein, what are you talking about? Of course, that makes sense. Yeah, if I updated that value, of course, a new transaction will pick it up. What are you talking about, right? This type of consistency, relational databases and NoSQL databases suffer from this, right? We cannot guarantee this. If we have one database, life is dandy, right? If you have one server, everything is nice and easy. Relational database is the best if you have one single server. But that's, in reality, you never have one server if you have like 1 million users. You need to scale. Lots of reads, lots of updates. You're going to add caches. You're going to add nodes, follower nodes. You have one leader node and one multiple follower nodes. And those follower nodes will take on your reads, and we'll have one reader or leader writer node, right? Let's take an example and talk about this eventual consistency concept, right? In reads, essentially, okay? So now, let's say I have this master node or the leader node, and then you have 2 follower nodes here, okay? That is essentially just getting whatever the master node or the leader node gets. They follow the values and will get propagated. Those values will get propagated to those follower nodes, okay? And we point the readers to this databases so we can offload this huge number of these million users to these databases, like put them behind a load balancer or something, and then just offload these huge number of reads, okay? Sounds good? Let's say I want to update Z, the value Z. Now, this is a consistent view. All of these databases are Z's, right? Have a value of Z. I'm going to update it. X, right? Okay, so sweet. My leader node now have a value of X. But guess what? At the same time, someone started to read that value, but they got what? They got Z. So now, this system is inconsistent to me, right? It's not consistent. Despite it being relational database, this is a Postgres database, right? 3 Postgres instances. It's not consistent. It is eventually consistent, and we're going to talk about that now. So we read that, we got an old value, we just broke our rule, right? We said when I write something and another transaction read it, it better get the latest value. It did not. And that is why we are inconsistent here in this case. Okay, this poor slob got an old value. Maybe that's okay, but we're just saying. Now, with time, X or the leader node will start pushing the new value to the follower node. This guy will push the new value, and now new reads will start reading the new value. So that's what eventually consistent system is. And this is a problem that is in both NoSQL and relational. So eventual consistency is not something for NoSQL databases, guys, okay? So we need to really clarify that. And first, what do you mean when you say consistency, right? What do you mean by a consistent system? Are you talking about the reads, or are you talking about the actual view of the data? Is it consistent in the data itself? Are they different tables? Because that's great. Yeah, that update might touch 7 tables in an atomic manner, in an isolated manner, and that view is consistent in this database, but the whole system to the user, it is not consistent because you introduce those new hubs. The same thing with if you introduce a cache, like a Redis or Memcached, right? The moment you introduce a cache, you're inconsistent. Whenever you have a cache, you're inconsistent because you will remain inconsistent unless you update the cache, okay? Once your data is in 2 places, you're inconsistent. You will become eventually consistent, which is, this is just a marketing term to me, right? It's just, yeah, of course it's eventual consistency. Yeah, in this case, yeah, eventually these values will get it, but it's up to you now as a user, as a software engineer. Can you tolerate that? Is that okay? Is that okay if the user read a value and they got 7,000 likes instead of 7,011 likes, right? On Kylie Jenner's latest picture, okay? Maybe not. I don't care, right? I don't care if that egg picture got 3,020,000 views. Is that even a number, right? On her picture versus the second person actually got, like, I don't know, an extra 50,000 likes extra. It doesn't matter, right? Sometimes it doesn't matter. Sometimes it does matter. If I updated my balance, right? If I deposited $1,000, I better see that $1,000, right? If I withdrew some, let's say if I withdrew some money, right? And let's say at the same time I did double withdrawal, double spend, and I end up with $2,000 while I have only $1,000 in my account, that's an inconsistent. It's good for me because I was able to trick the bank and draw $2,000 while I have only $1,000, right? Because of this inconsistency, and that's something bad, right? So that's eventual consistency in a nutshell, right? Let's talk more about the consistency in reads. If a transaction committed a change, will a new transaction immediately see that change? That's what a consistency in reads mean. It's different than inconsistency in data. I don't know if there are times I made those two terms up, okay? This is the real thing. I don't know if they have an actual scientific term, right? But what do you think about it? That's the only thing I can think about it. There's a data consistency and there is read consistency. And you have to clarify the two differences, okay? It's a problem in both SQL, NoSQL, and relational, right? As long as you want to scale horizontally and introduce caching, right? With NoSQL databases, and if you have sharding, that's a different story. We're not going to talk about sharding in this video, right? But that's in a nutshell. The moment you introduce caching or you try to scale horizontally by adding some follower nodes, you are inconsistent. That's eventual consistency in a nutshell, guys. So summary, what did we talk about? We talked about consistency. We talked about the different two types of consistency, right? We talked about consistency in the data. We talked about consistency in reads, right? We talked about how those two differ, right? Consistency in the data is guaranteed by this property that's called atomicity and isolation and even durability, if you think about it, right? So it's like if I commit and I rate it again, it better be there, right? If it's not there, then it's not durable, then it's not consistent, if you think about it, right? And eventual consistency is the ability for the reads only, right? This is a point I forgot to mention. If you screw up your atomic transaction, you have like 7 tables, they have to stay consistent together, right? And you updated 3 and you got blue screen of death. There is no eventual consistency coming out of that, dude. You just screwed, you corrupted your database. There is no eventual consistency in that. If you do not have atomicity, you do not have eventual consistency. You do not have consistency at all. Consistency in read is different than consistency in the data. A consistent read, yeah, sure, I'm gonna commit that. Eventually, that follower node, if it's offline, gonna come online and it's gonna pick up the new data. That's okay. We know that's gonna be, because we know that this side, we guaranteed the consistency at that leader node. But the moment you screw up, you don't have isolation, you don't have proper atomicity, you don't have durability, no eventual consistency can actually help you here, my friend. All right, so your data is done. Okay, you have corrupted inconsistent data. If you have inconsistent data, there's no point of doing an inconsistent read because your view will always be inconsistent no matter how long you waited. And I'm gonna see you in the next one. You guys stay awesome.